Here is Lesson 8, the long division algorithm. In this lesson, we move toward being able to define an irrational number by formalizing the definition of a rational number. By the end of this lesson, we will know that the long division algorithm is a basic skill to get division with a remainder and the decimal expansion of a number in general. We will know why digits repeat in the decimal expansion of a fraction by using the long division algorithm. We will know that every rational number has a decimal expansion that repeats eventually. An interesting fact, there is no single long division algorithm. The algorithm commonly taught and used in the US is rarely used elsewhere. Alright, so let's take a look at example 1. We're going to show that the decimal expansion of 26/4 is 6 5/10. We will use this model to complete exercises 1 through 5, so please pay attention and copy down the steps. Show that the decimal expansion of 24/6 is 6 5/10. You will most likely use the long division algorithm. Division is really just another form of multiplication. Here is a demonstration of that fact. Let's consider the fraction 26/4 in terms of multiplication. We want to know the greatest number of groups of 4 that are in 26. How many are there? Well, there are 6 groups of 4 in 26. Is there anything left over, a remainder? Yes, there are 2 left over. So symbolically, we can express the number 26 as 26 being equal to 6 times 4 plus 2. Notice that this is multiplication and addition, not a division problem. So with respect to the fraction 26/4, we can represent the division as 26 over 4 is the same as 6 times 4 plus 2 over 4, which, using the addition part and having to create common denominators, that means 26/4 can be represented as 6 times 4 over 4 plus 2 over 4. When we do this, the 6 times 4 divided by 4 becomes 6, and the 2/4 becomes the fraction. And because 6 2/4, or 6 plus 2/4 is another way of saying 6 2/4, the mixed number, then we reduce it and we get 6 1/2. So the fraction 26/4 is equal to the finite decimal 6.5. When the fraction is not equal to a finite decimal, then we need to use the long division algorithm to determine the decimal expansion of the number. Alright, exploratory challenge, and this goes with exercises 1 through 5. Go ahead and complete these and continue the video to check your answers. Alright, you should be done with exercises 1 through 5. Go ahead and check the answers, again making sure you fill in the blanks according to the model that we used in the example. Alright, let's have a quick discussion. Again, you can synthesize any information you need to in your math journal. So what is the decimal expansion of 142 over 2? Well, if you respond with 71, then what decimal digits could you include without changing the value of your number? Well, the fraction 142 over 2 is equal to the decimal 71.0 repeating. Did you need to use the long division algorithm to determine your answer? Why or why not? No, the long division algorithm was not necessary because there was a whole number of 2's in 142. So what is the decimal expansion of 142 over 4? Well, the fraction 142 over 4 is equal to the decimal 35 and 5/10. So what decimal digits could we include to the right of the 5/10 without changing the value? Well, we could write the decimal as 35.50 with the 0 repeating. Did you need to use the long division algorithm to determine your answer? Why or why not? No, the long division algorithm was not necessary because 142 over 4 is equal to 35 plus 2/4, and the 2/4 is a finite decimal. We could use what we learned in the last lesson to write 2/4 as 5/10. So what is the decimal expansion of 142 over 6? Well, the fraction 142 over 6 is equal to the decimal 23.6 repeating. Did you need to use the long division algorithm to determine your answer? Why or why not? Well, yes, the long division algorithm was necessary because 142 over 6 is equal to 23 plus 2/3, and 2/3 is not a finite decimal. Note, you may have recognized the fraction 2/3 as 0.6 repeating because it is a benchmark fraction and not used the long division algorithm to determine the decimal expansion. How did you know when you could stop dividing? Well, we know to stop dividing because the remainder kept repeating. Specifically, when we used the long division algorithm, the number 40 kept appearing, and there are 6 groups of 6 and 40, leaving 4 as a remainder each time, which became 40 when we brought down another 0. We represent the decimal expansion of 142 over 6 as 23.6 repeating, where the line above the 6 is the repeating block. That is, the digit 6 repeats as we saw in the long division algorithm. So what is the decimal expansion of 142 over 11? Well, the fraction 142/11 is equal to the decimal 12.90 with the 90 repeating. Did you need to use the long division algorithm to determine your answer? Why or why not? Well, yes, the long division algorithm was necessary because 142/11 is equal to 12 plus 10/11, and 10/11 is not a finite decimal. How did you know when you could stop dividing? Well, we knew to stop dividing because the remainder kept repeating. Specifically, when we used the long division algorithm, we kept getting the number 10, which is not divisible by 11. So we had to bring down a 0, making the number 100. This kept happening, so we knew to stop once we noticed the work we were doing was the same. So which block of digits kept repeating? The block of digits that kept repeating was 90, or 90. So how do we represent the decimal expansion of 142/11? Well, the decimal expansion of 142/11 is 12.90 with the 90 repeating. So in general, we say that every rational number has a decimal expansion that repeats eventually. It is obvious by the repeat blocks that 142 over 6 and 142 over 11 are rational numbers. Are the numbers 142 over 2 and 142 over 4 rational? If so, what is their repeat block? Well, the decimal expansion of 142 over 2 is 71.0. And the 0 repeats, where the repeating block is 0. The decimal expansion of 142 over 4 is 35.50 repeating, where the repeat block is 0 again. Since the numbers 142 over 2 and 142 over 4 have decimal expansions that repeat, then the numbers are rational. All right, exercises 6 through 10. Go ahead and complete these exercises and then check your answers. All right, you should be done with the exercises. Go ahead and check your answers. If you have any questions, make a note and bring them to class. All right, let's wrap this up. We know that the long division algorithm is a procedure that allows us to write the decimal expansion for infinite decimals. We know that every rational number has a decimal expansion that repeats eventually. All right, we'll see you in class.